Have you ever wondered how we can determine so much about objects in the universe? Like the sun, how do we know that it's made up of 74% hydrogen? Or that its surface temperature is almost 6,000 Kelvin? Or that the sun rotates once every 24.5 days? The answers to all these questions can, in some way, be tied to a field of science called spectroscopy, which is the study of light and its interactions with matter. When a scientist observes and records light, they produce a spectrum, or many spectra, which tell them how much of each color or wavelength of light is produced by the objects they're studying. When an astronomer produces a spectrum, they are spreading incoming light into a band of colors, just like you see when light from the sun is spread into a rainbow. This is exactly Newton's famous prism experiment, where he demonstrated that white light is actually a combination of every color of the rainbow. An astronomer collecting spectral data is doing much the same thing, the act of separating light into its component colors. Only modern equipment uses special instruments called diffraction gratings. Just like Newton's prism, a diffraction grating separates light into its component colors. However, diffraction gratings use the physics of waves to spread light out instead of refraction. An example of this is the interference on a compact disc. The rainbows produced are from the interference of light rays reflected by the lines etched on the CD's surface. Spectrometers can be combined with telescope technology for use in astrophysics. Telescopes equipped with spectrometers can do what's called imaging spectroscopy. By collecting a spectrum for each pixel of an image, scientists can distinguish what colors are produced in different locations on the same object. A spectral image is a type of image that allows us to do very special things. Even to regions which look the same to our eyes, if we examine their spectra overlaid on one another, there can be noticeable and important differences. From a spectral image, we can extract a wealth of information about different parts of astrophysical objects. Since each pixel corresponds to a different location in the sky, we can examine all the different parts of what we call extended sources. An extended source is something that doesn't appear point-like to us. They extend over a region of the sky. Extended sources appear to be large, either because they are big or because they are very close to us. Some examples of extended sources are the sun, a nebula, or even a galaxy. Spectroscopy is one of the most frequently used tools in an astronomer's toolbox. Without spectroscopy, we would struggle to define important characteristics of the objects we view, speeds, temperatures, and compositions, to name a few. When matter in outer space interacts with light, we see the results as a spectrum. In astrophysics, we discuss three primary types of spectra, summarized by Kirchhoff's three spectral laws. The first of Kirchhoff's laws describe the conditions for blackbody emission, while the other two laws deal with atomic emission and atomic absorption, which we'll cover in the next lesson. Kirchhoff's first law states that a luminous solid, liquid, or gas emits light at all wavelengths. This law is a description of the type of light given off by blackbody emitters. You're probably familiar with at least one type of blackbody emitter, your kitchen stove. If it has electric coil burners like mine does, it will emit a deep red light when you're cooking. This might be confusing since Kirchhoff's law says it should emit light of all wavelengths. Well, blackbodies do emit light of all wavelengths, just at vastly different intensities. For example, there are so few X-rays being emitted at this temperature that we can totally ignore that part of the spectrum. On the other end, the burner feels hot because along with a lot of red light, the burner is also emitting plenty of infrared light. The spectra of thermal or blackbody emitters are continuous, like rainbows. You may remember from Module 2 that blackbodies absorb all incoming light across all wavelengths and are completely non-reflective. The kind of light they emit will depend solely on their temperature. This temperature effect can be seen when examining a fire poker as it gets hotter and hotter. First, there is red hot, then orange and yellow hot, and finally white hot. The surfaces of stars, which are close approximations to blackbodies, exhibit the same properties, though they can get even hotter, getting to blue hot for certain types of stars. As the thermal emitter gets hotter, its peak emission is shifted into more energetic portions of the electromagnetic spectrum. Black hole accretion disks can be so hot that their peak emission isn't blue hot, it isn't ultraviolet hot, it's X-ray hot. When plotted, blackbody spectra are smooth, continuous curves that look like the hill of a roller coaster. Let's see how changing the temperature of a blackbody emitter changes its spectrum. Two laws govern the shape of a blackbody spectrum. The first, Stefan-Boltzmann law, states that a hotter object emits more light at every wavelength. What does this mean for our plot? Well, higher temperature, larger curve. Additionally, the second law, Wien's law, states that a hotter object emits light with greater average energy. What does this mean for our plot? Well, A change in temperature will skew the peak of this graph. Hotter objects move the peak towards shorter wavelengths, higher energies, and lower temperatures will move the peak towards longer wavelengths, lower energies. Recall that frequency and wavelength are inversely related, so the same graph plotted for frequency instead of wavelength will look reversed. A higher temperature means that peak emission of a hotter object is shifted right towards higher frequency, which is more energetic. Kirchhoff's second and third laws are concerned with how emission and absorption spectra are produced. Producing these types of spectra relies on a process which affects individual atoms and molecules, called luminescence. Luminescence is the process that produces light when electrons drop from higher energy states within an atom or molecule to lower energy states. Kirchhoff's second law states, a low-density hot gas seen against a cooler background emits a bright line or emission line spectrum. As we mentioned before, luminescence is responsible for this. When electrons transition from higher energy states to lower energy states, they emit light based on how far or how many states they drop. The reverse process can also happen, which is described by Kirchhoff's third law. A low-density cool gas in front of a hotter source of a continuous spectrum creates a dark line or absorption line spectrum. So, if the right energy of light is shining through a low-density gas like a nebula, electrons can steal energy from passing photons in order to climb to the higher energy states. By absorbing light, the low-density gas, cool gas, takes away portions of the continuous spectrum of the background emitter, leaving behind dark absorption lines. Energy level transitions are an effect of quantum mechanics. Electrons surrounding the nucleus of an atom are able only to accept quanta, or in other words, specific amounts of energy. When a passing photon or a collision between atoms in a gas has the right amount of energy, the electron will transition to a higher energy state. Transitioning to a high energy state is much like climbing a ladder. You can only exist at the top of each rung. You can attempt to place your foot in between the rungs, but all that will result in is a banged up shin. Shortly after an electron transitions to higher energy, it spontaneously transitions back down to a lower energy state. The energy the electron had has to go somewhere. And what happens is the atom produces a photon, which is the same energy as the difference between the higher energy state and the lower energy state. A large number of these downward transitions will produce a bright emission line in the spectrum, and a large number of upward transitions will produce a dark absorption line. It's important to note now how we can determine chemical composition using emission and absorption spectra. Each type of atom or molecule has a unique set of energy levels which produce a unique set of emission lines, meaning each type of atom or molecule can be characterized by a unique spectrum. This is a lot like the fingerprints on your hand. Every person has a different set of fingerprints, and every type of atom produces a different emission and absorption spectrum. A lot of work has been done by scientists to study the spectra of atoms and molecules in the lab, so we know very well what they look like. When we look at an object in the sky, we can match parts of its spectrum to specific atoms and molecules to determine what it's composed of. Here's a great diagram that helps us explain Kirchhoff's three laws. If a light source, like a star, is shining through empty space, we see the blackbody spectrum it produces as a continuous rainbow of colors, like in the leftmost image. If the star has a cooler outer atmosphere, or photosphere, then some of the cold atoms will absorb photons with specific colors, causing electrons to move to higher energy states. This removes light from the continuous spectrum of the background source, creating an absorption spectrum, as shown in the center image. If instead, light from a star strikes a nebula from the side, electrons will be excited and subsequently fall to lower energy states. In doing so, they will emit light with specific frequencies in all directions, including ours. This process produces an emission-like spectrum, like in the rightmost image. Keep in mind that we are generalizing the emission and absorption processes, and that both can happen simultaneously and are only mediated by the temperature of the object. Both emission and absorption spectra are important in determining the chemical abundances of objects in space. We examine how bright emission lines are, or how dark absorption features are, and how each is associated with a different element or molecule to determine how much and what is prevalent in all sorts of astrophysical objects. This is the first step in characterizing a black hole system, but advanced techniques can tell us even more.